So now we're going to be looking at polarity of whole molecules. We looked already, so let's remind ourselves, we looked already at polarity of bonds. Like we said, a CO bond is polar. Anybody want to give us a quick, in your words, version of why that's polar? What's polar about a CO bond? What happens in a CO bond? No, in this case, they're both nonmetals. What's going on with the electrons? The electronegativity, yeah. The electronegativity is a measure of what happens. What actually happens? The what? Carbon's bonded to oxygen, and what happens within those two electrons in those bonds, in that bond? It's pulled more toward the oxygen, right? Yeah. So in a bond between carbon and oxygen, the electrons are pulled more toward the oxygen and away from the carbon, and that leads to a separation of charge, where we have a partial negative charge on the oxygen and a partial positive charge on the carbon. All right. So we talked about that. We talked about the different electronegativity values, and we said that something like a CH bond we called nonpolar because there isn't a significant difference in electronegativity. The electrons are not pulled more toward one atom or toward the other. So that is a nonpolar bond. All right. So now we want to extend that to what happens if you have an entire molecule that's made up of these bonds. How do you decide if that whole molecule is going to be polar or not? So what you do, we'll start with a molecule that is made of these bonds that we just talked about. This is a molecule called formaldehyde. So the first thing you need to do is you need to know the shape of the molecule. And we skipped that section in the book about how to determine the shape of the molecule because we're not going to get into that. But I will sometimes give you the shape of a molecule. You can look at a molecule like this. And we can analyze the overall polarity of this molecule by looking at the individual bonds. So the overall polarity has the same definition as the bond polarity. The molecule is polar oops, I should get plural. Molecule is polar if there are positive and negative sides. So in other words, there's separation. There's like a positive on one side and a negative on the other side, like that. And that could be in any orientation. It could be like this or whatever. But for something to be polar, it means it has a positive side and a negative side. So in the bond, we just look at the two atoms and we say, okay, is there going to be are the electrons pulled to one side or the other? If they are, then it's polar. In the whole molecule, well, we need to do a little bit more work than that because the molecule is made up of all different bonds. We have to see if they're polar, and then we have to kind of take it all together to see if the entire molecule is polar. So let's see how that works. In this molecule here, we would analyze each individual bond. So we look first at the CO bond, and would you say that's a polar bond? It is, like we just talked about. So you can draw that on there. Partially negative on the oxygen, partially positive on the carbon. And then what about the carbon and hydrogen bonds? Are those going to have any polarity? They're not, because there's not a significant difference. So that's it. So we wouldn't draw any more positives and negatives on that molecule.
Does double?
No, it doesn't. It is different in lots of various ways, but for this, it doesn't matter, right? So then once we've added all of the partial charges onto the molecule, then we say, all right, well, can we separate this molecule And we draw a line through it so that it has a negative side and a positive side. So what do you think? Can we draw a line through this molecule and give it a negative side and a positive side? Down in your head? Okay. Yeah? How would you draw that line? Yeah, so we could draw a line kind of like this. And we would say that top half is where the negative stuff is, and the bottom half is where the positive stuff is. And so this molecule is overall polar. Yeah, that works a little bit. Let's try another one. Look at water. Water can be drawn various ways, but it always has this bent configuration. The angle is about 105 degrees between from hydrogen to oxygen to hydrogen. So that's the shape of a water molecule. So I want you to do the same analysis on your own or with a partner. Analyze each bond, draw in the negative and positive, and then decide if the negatives and positives are on opposite sides of the molecule. Where you can draw a line some direction, doesn't matter what way, but you can draw a line some way that separates the negative charges from the positive charges. First question, I guess, is an OH bond polar? Is there a charge separation between H and O? Yes, anything with O is always going to be polar. Unless it's another O. So, yeah, use that information, draw those out, see what you come up with, and then we'll look at it together. Maybe lose their glasses. Their glasses now. Sorry. All right. All right, so what kind of positives and negatives did you draw here? Right, so we look at each individual bond. Got positive here and negative here. Whoops, negative there. Over here, same thing, positive and negative. Oxygen's very highly electronegative, so that's pulling the electrons toward itself. So now with those drawn, can you separate the molecule into a positive and a negative side? Does everybody see that you can? Where would you separate it? Everybody draw with your hand. How would you do it? Yeah? Yep. Yep, that's right. So you go like this. And the positives are on this side, negatives are on this side, so that makes it polar. You good? All right. Look at another one. This is carbon dioxide. Oh, just for consistency, we should write that this is also polar. All right, there's carbon dioxide. Carbon dioxide is a linear molecule, which means it just goes straight across OCO. Same question, same thing. Analyze the bonds, analyze the overall molecule. Can you separate it into a positive side and a negative side?
How are you getting the positive for the H?
O is more electronegative. It's up toward the right there, the NOFCl. So that's the one that pulls the electrons more. All right, so what'd you get for this one? Polar or not? Shaking your head. Why not? What? Oh, I meant like bonded to each other. Like if you had an OO bond, that would be polar because they wouldn't share the electrons back and forth. These are still CO bonds, which makes them still polar bonds. So we can still write that there's a, oops, let's keep our colors here. There's still write that there's a negative here and a positive here, and then positive here and negative here. So we can still analyze those two bonds. So now, is there a negative and a positive side of the molecule? Maybe. So how would you cut the molecule to get a negative and a positive side? Straight through the carbon, how? Like what direction? Like this?
Because there's still positive sides.
Okay, so if I cut it like that, which side is the positive side and which side is the negative side?
Oh.
Yeah, but there's an oxygen on each side. So if we're looking at the overall molecule, so there's a problem here. Yeah, so they kind of cancel each other out. Because you can't really find a positive and a negative side here. You see that? It's like the outside is positive, or the outside is negative and the inside is positive. But that's not something where you can draw a line and say we've got positive on this side and negative on this side. So when you have this situation, even though there's polar bonds inside there, we would say that overall the molecule is not polar. So when you have these like perfectly symmetric molecules where you have the same stuff all around something in the middle, those are not polar even if the individual bonds are polar themselves.
So the last thing here, the last electronegative, get the plus.
Mm-hmm. Right. All right, so most of the time, this is not an issue. Usually, when we talk about polar versus nonpolar, the nonpolar thing is nonpolar because it doesn't have any polar bonds. So most of the nonpolar materials that we're going to be worried about, we're going to be dealing with, are things like we're going to do next week in lab, are things like this. So a molecule is made up of lots of carbon and hydrogen. This, we would say, as a molecule is nonpolar because it doesn't have any polar bonds inside of it at all. So there's no real separation of charge anywhere. Usually, it'll be between that and between stuff like this. These perfectly symmetric small molecules where everything cancels out are kind of unusual. There's a handful of them, but I mostly just put that in there to make a point. The ones that we're going to be focusing on are things like this and this. All right. So does that sort of make sense in terms of how you can predict whether a molecule is going to be polar or nonpolar based on its bonds? Okay. All right. So the reason for doing that is not just so we can classify molecules in one category or the other. The reason it's so important is because whether or not a molecule is polar affects how it interacts with other molecules. And how it interacts with other molecules is something called intermolecular forces, or IMFs. Intermolecular forces are how molecules attract each other. And these are so important because this is how condensed states exist. That is everything except gases. So in gases, in a gas state, all molecules that are in the gas are just flying around independent of one another. There's lots of space between them. Occasionally they hit each other, but they're mostly just separate from each other. Then when we condense them into liquids and solids, that's no longer the case. In liquids and solids, the molecules are actually attracting each other and holding on to each other and holding each other together. Remember the definitions of liquids, solids, and gases? What's the difference between a liquid and a gas?
Liquids take the shape of their container. Is that it?
Well, they both take the shape of their container. But you're right, you're on the right track. What's the other thing about that? Remember? Yeah, but what is it about, like, so if you have two substances and you wanted to know, or you wanted to explain to someone why one was a liquid and one was a gas, what is the important difference between the two? What is the important thing that separates a liquid from a gas? Not necessarily, because you can have gases and liquids and whatever temperature, depending on boiling points. Well, that's true, but we can't see that. We mean like in the bulk phase. Like if you're just looking at it, how can you tell a gas from a liquid? That could be true but some gases are colored. Some gases you can't see. But you're right, in most of our experience, gases are clear, you can't see them. And sure. Yep. No, that's the thing. It's like, it seems like a basic kindergarten thing, but it's really pretty difficult to define. Like, we all know what gases and liquids are, but to actually put it into words and say, this is what a liquid is, and this is what a gas is, and this is why they're different, is tricky. No?
Liquid's wet.
That's not true of all liquids.
I drink gas.
Can't drink gas. There's a lot of liquids you probably shouldn't drink either. All right, so here's how it works. I got a beaker here, 100 milliliter beaker. What is inside this beaker right now? Air, right? How much air is inside this beaker?
100 milliliters.
100 milliliters, because it's full of air, right? So now I'm going to put some water in there. Water's a liquid. Snake was really mad about me doing that.
Is it the capability of?
Yeah, you're on the right track. So how much water is in this beaker? I don't know if you can see, but
Like
people in the front, about how much water is in here. Yeah, it's like 8, oh no, it's 16. So it's up to the 60. So there's about 60 milliliters of water in this beaker, right? In the gas they are. The thing about, all right, so when we had this beaker filled with air, there was 100 milliliters because it was all full. Could we fill this beaker with only 40 milliliters of gas?
No.
Can't, because it would always fill the whole beaker. If this has gas in it, it always has 100 milliliters of gas in it. You can't put this much gas in it and then leave the rest empty. So gas will always take the entire volume of its container. But liquid has a fixed volume. This is 60 milliliters of water no matter what container I put it in, right? If I pour it out on the counter here and it just like starts spreading out, it's still 60 milliliters of water. It hasn't changed its volume. It'll change its shape, but it doesn't change its volume. So that's the key difference between a gas and a liquid, is that a gas always takes the shape and the volume of its container. A liquid takes the shape of its container, but it has a fixed volume of its own. All right, so that's the next one. So what about a solid? Using those same types of definitions, what's the difference between a solid and a liquid?
Fixed and it doesn't.
Right, it has a fixed volume and it also has a fixed shape. It does not take the shape of its container. So if I put a solid in the beaker, it maintains its own shape. That makes it solid. So that's the key difference here. And the thing that allows for that to happen is these intermolecular forces. A gas always takes the entire volume of its container because the molecules don't attract each other at all. So they can spread out as much as they want to fill whatever space they're in. A liquid can spread out a little bit because the forces are, let's say, medium strength, whatever that means. And then a solid is fixed with extremely strong forces. Much stronger forces, we should say. So we're talking about condensed forces, and we're going to talk primarily about liquids. So for an example, let's look at water. Water in the liquid form, if we zoom down at the molecular level, would look something like this. Well, you know what? Let's see if we can find a good picture of it, because I don't think there really is one in the book here. See if we can find one that's right. This is good enough. So here's an example of what this might look like. This is just a diagram. It's not exactly correct. But you can see in liquid water, you've got all these water molecules that are sort of in random orientation at different distances from the other water molecules, but they're connected with these dotted orange lines that are kind of holding them together. And then in the solid, you have these same dotted orange lines connecting the water molecules, but they're more organized. See that organization? They're in this hexagonal structure, and they're like kind of fixed in place. And for all of the molecules are the exact same distance. I don't know if you can see that in the diagram exactly, but all those orange dotted lines in the solid are the exact same length. So everything's kind of fixed in the same place. Whereas in the liquid, there's all different lengths. There's varying different lengths of those connections. Those connections are called intermolecular forces. And we'll talk specifically about the type that they are in a minute, but they're not bonds. They're not covalent bonds. They're weaker than covalent bonds. They're farther apart than covalent bonds. The covalent bonds are the ones that are actually so short they're not even shown here. You see that? There'd be those two, the HO connections way in here. So what do you think, if that's the liquid and that's the solid, what does the gas look like? How would the gas be different than from those two pictures? Yeah, the molecules would be spread apart even more. And would there be any orange lines connecting them? None at all. So there would be no connections between the molecules. So when water boils then, what's happening? When you put all that energy into water to get it to boil, what are you doing? What is that energy doing? What is it breaking? Yeah, the intermolecular forces, the orange things. This is a really important point that a lot of people get mixed up with a little bit. When you boil something, remember that is a physical change, not a chemical change. You're not changing what that thing is. And so that means that you're not actually breaking any chemical bonds. Because as soon as you break a chemical bond, you've made a chemical change. You've changed the identity of something. So you can't break chemical covalent bonds when you boil something. Instead, you break the intermolecular forces. You separate the molecules from each other, and you break those forces. Yeah, sure. So like, if you heat oil in a, well, here's sugar is even a better example. Has anybody ever heated up sugar, like to make caramel or candy or something? All right, so you're heating up the sugar. For those of you who haven't done it before, what happens? What's like the process? Anybody want to give us a description of like what happens? What? Instead of bubbling, it's thicker and thicker and thicker and thicker. Does sugar boil? It doesn't actually boil. What happens once the water's done? You keep heating sugar, You just keep heating it. What eventually happens? It burns. Yeah, it turns black. You ever seen that? Like you don't take it out just right when you're making caramel or something. You leave it on there, it starts turning brown, and then it turns black, then it smokes, and like ruins your pan, and it's just terrible. Well, that's because sugar, actually, the bonds in sugar, the internal covalent bonds, break before it boils. So you're actually breaking down the sugar and decomposing that sugar before you actually boil it. So in that case, you're breaking the bonds before you break the intermolecular forces. And some compounds do that. Their bonds actually break before they separate from one another. So that's an example of that. But then you can see that's a chemical change, because that black stuff is no longer sugar, right? I don't know if you ever don't eat it, but if you do, you can eat it. It's not like bad for you, it's just kind of gross. But it's definitely not sugar. So you changed it. But when you boil water, you can put as much heat as you want into that water. It's not going to break the OH bonds. It's just going to separate the molecules, the O and the H, or the H2O molecules from each other.
So then how can you make the statement that intermolecular forces are weaker than the covalent bonds if at sugar the bond breaks before the force?
Yeah, good question. What's happening there is individually, compared one-to-one, intermolecular forces are much weaker. But in something like sugar, they have this whole network of forces that all together ends up being stronger. And then the stability of the breakdown products and other things are going on too. But yeah, when taken all together, they can actually become quite strong. But individually, compared to those bonds, they're not. All right, so then in the gas, these would be separated, but the bonds would not be broken. We're talking now about physical changes, about boiling. Okay. Let's talk about the two basic types of intermolecular forces, the polar forces and the nonpolar forces. So this is why we just spent all that time figuring out if molecules are polar or not, because predicting the types of forces they're going to have requires that we know if they're polar or not. So polar molecules attract each other kind of in the way that you would expect. The positive sides of the molecules interact with the negative sides of other molecules, and they attract each other because positive and negative attract each other. So if we had a water molecule like this, actually, we'll look at water in a second because it's a little bit special. Let's look at HCl instead. If you have an HCl molecule like this, Cl is in that highly electronegative area, right? So we have a partial negative on Cl and a partial positive on hydrogen. That's the whole molecule, so that clearly has a positive side and a negative side. And then another HCl molecule can come along next to this and line up with opposite charges. So again, the positive side, the negative side, and we would expect an intermolecular force between those two, like that. And that could keep going on and on. So another one would be over here. And so on. So those are those polar forces. There's our polar IMF, holding those things together, negative and positive. So that's how polar molecules hook together. There is one special type of compound, and we talk about it because it's actually pretty common, but it's very special, and that is something like water. When a molecule has hydrogen connected to oxygen connected to nitrogen or connected to fluorine, we say that it can, and this is a terrible, terrible phrase, we say that it can hydrogen bond, or it has hydrogen bonding. Hydrogen bonding is a special kind of polar force that is exceptionally strong, much stronger than any other types of intermolecular forces. The reason I say it's a terrible, terrible word is that it has this word bond in it. It sounds like it should have something to do with a covalent bond, but it doesn't. It's an intermolecular force. And keeping that straight can be really confusing. So make a note to yourself, whatever you need to do, remember that hydrogen bonding and hydrogen bonds is not a it's not a type of covalent bond. It's a type of intermolecular force, a type of polar force that holds molecules together. And this is what we have in water. So when we draw the connections between water, it's actually quite a bit stronger than the connections between HCl. Here's our negative and positive there, which then connects with another molecule of water. Which then connects to another one, and this is what we see in that diagram, that picture from above. So this intermolecular force is called a hydrogen bond. Which is much stronger than the regular old polar forces above. But it is still a regular polar force of positive and negative attracting. So this is why water has a high boiling point compared to other molecules of its size. So we can judge the strength of intermolecular forces by boiling points because of all the reasons we just talked about. When you boil something, you separate the molecules from each other. So the stronger those forces are, the more energy it takes to pull those things apart, the higher the boiling point. So boiling point is a good measure of intermolecular force strength. What's the boiling point of water in Celsius? 100 degrees C, right? Okay. If we look at methane, which is nonpolar, actually I have to look this one up. It's minus 161 degrees C. So CH4 is about the same size as H2O, same kind of size molecule. But the connections in water are so much stronger that the boiling point is way, 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 way higher. Methane is gas. Methane is the major component of natural gas, CH4. And we know that's a gas at room temperature, and actually it would still be a gas until you got all the way down to minus 161 degrees. That tells you that the forces that connect those methane molecules, which we'll talk about in a little bit, the nonpolar forces, are much, much weaker than the polar forces connecting those water molecules together. Does that make sense? Okay. So we'll talk about the polar or the nonpolar forces, and then we will use this to judge boiling points, and if we still have time, how they connect to each other.
How is something in a negative?
that is the temperature where it switches from liquid to gas. That's what the boiling point is, right? I mean, it's a little more complicated than that, but that's what we call the boiling point. So that means that if you cool methane down to below 161 or negative 161, then it would condense. Just like with water, when you cool it down below 100 degrees, it condenses something. All right, so let's look at the nonpolar forces. The nonpolar forces between molecules are called dispersion forces. And actually, all molecules have them, but the polar forces are so much stronger that we usually don't worry too much about the dispersion forces in polar molecules. But they're the only kinds of forces present in nonpolar molecules. And they're a little weird because based on all the stuff we've said before, if methane is totally nonpolar, then it shouldn't have any way of attracting other methane molecules. But down below 161 or minus 161C, it does still attract other ones, and they still make a liquid, and you can actually condense it all the way down to a solid if you wanted to, if you can get cold enough. So there is something that holds nonpolar molecules together, even if that thing is much weaker, and that thing is called dispersion forces. But what dispersion forces are is they are a momentary asymmetry of electrons. So let's say we have an atom. There's our atom. And there's its nucleus in the middle. And its electrons will be, let's say it's helium, because helium atoms work for this. So a helium atom would have how many electrons? 2, right? And those electrons would be somewhere in that first shell, somewhere in that first sphere around the nucleus. They could be here and here. They could be over here and over here. There's any number of random ways that those electrons could be distributed, right? Because they're always moving around, so they're just kind of distributing themselves in random ways. In the first 2 examples, the electrons are on opposite sides of the nucleus. But in the third example, they're both on the same side. See that? So at that very instant, which is, the tiniest fraction of a second, at that very instant, there actually is a very slight separation of charge, where there's a little bit of negative down here and a little bit of positive up here where the electrons are not there. So just the electrons being a little bit lopsided in the atom causes a really, really small bit of polarity to happen right away. But as soon as that happens, if there are any other atoms nearby, they're suddenly going to line up. So we know that negative charges, electrons repel other negative charges. So electrons are going to repel electrons. So as soon as those 2 electrons end up on one side of the atom just randomly, then the electrons on the next atom are going to get pushed to kind of move away from those first ones. And then that one's suddenly going to have a little bit of a polarity too. And so on. It's going to create this chain reaction where all the atoms around, the electrons are going to get kind of pushed away. So you end up with this slight bit of polarity and this slight bit of connection. And that slight bit of connection is called dispersion forces. So that's actually enough. If you get enough electrons around, it's enough in a low enough temperature, it's enough to hold those molecules together. So a few things we should know about dispersion forces. They're much weaker than the polar forces. As you saw in the low boiling point for methane. or here, we should say the strength depends the strength is going to depend on the molecule size, a little bit on the shape too, but we're not really going to get into that. The size will be enough for our purposes right now. I'm just trying to look up some numbers here. 338. So here, I'm going to show you this table from the book. Sorry, I have to reload this to get it again. So here are some different molecules, and we'll get into this. This is from a later chapter. We'll get into this later. But I want you to look at this last column of boiling point as it scales with the size of the molecule. So don't worry too much about the structures, but you start with methane, whose boiling point is way down at minus 162. And then as you add carbon and hydrogen atoms to these molecules, the boiling point increases and increases and increases. Once you get to octane, you actually have a boiling point now that exceeds that of water. It's 125. So that tells you that eventually, when the molecule gets big enough, the dispersion forces are strong enough to hold it together in a liquid at room temperature. And then actually, as you get even bigger and bigger and bigger, well, this doesn't show that, but so this is 10 carbons and 22 hydrogens. As you get up into the 20s and up of carbons, you actually start making solids at room temperature, and that's what we know as waxes. So things like paraffin, like candle wax, those are totally nonpolar, but because the chains are so big, they have enough dispersion forces to actually hold them together and make a solid. So very big nonpolar molecules can still have high boiling points, but for comparable sized molecules, the dispersion forces, the nonpolar forces, are going to be much weaker. All right, so those are the main types of forces that we're going to worry about. Let's talk about using them to judge or predict chemical properties. So we're going to look at boiling points, and we're going to look at solubilities. Let's look at judging relative boiling points. There's two factors that you're going to use in this order. First is the type of intermolecular force, and second is the size of the molecule. So you're going to look at a molecule and say, all right, if this has polar forces, if this has hydrogen bonding forces, it's going to be much, much stronger held together in the liquid phase, and therefore it's going to have a higher boiling point, something like water, than if it's nonpolar. If two compounds have about the same type of intermolecular force, then we're going to look for whichever one's bigger. The bigger one's going to have the higher boiling. So under type of intermolecular force, we're looking specifically for hydrogen bonding, or other polar forces will lead to a high boiling point because those connections are so much stronger. And for size of molecule, but to avoid problems, make sure that you think of these things in that order. The type of intermolecular force is a much greater effect than the size of the molecule effect. But the size of the molecule effect is more obvious, so people like it more. But don't make that mistake, because it's easy to see if a molecule is bigger or smaller, but that's not as big of an effect as the type of intermolecular force. So let's make a little star here that this is the most important. This has the biggest effect on the boiling point, not the size of the molecule. We only look at the size of the molecule if the types of forces are the same. Okay. So let's look at some examples from the book here of judging different boiling points. Okay, here's two molecules that are the exact same size, made of the exact same atoms. And we're going to decide which one has a higher boiling point than the other. So these are kind of big molecules, big organic molecules. We're going to compare that one versus this one. And we want to know which one has the higher boiling point. Which one would you expect to have the higher boiling point? So for this one, talk in your groups of 4, 3, here, I guess 4 for 3. Talk in your groups and decide which one has the higher one, and more importantly, why? What's the reason for that? And I'll ask a couple of groups for what you said. All right, so how many people said the first one would have the higher boiling point? How many groups said the second one? How many groups couldn't decide? Everybody's sort of decided. Okay. So let's talk about those reasons. All right, you all said the first one. What was your reasoning for that? Hydrogen bonding with what?
Hydrogen.
So what does that do? Okay. All right, thanks. So somebody who said the second one. Why the second one? Okay, what does being symmetrical most often lead to in terms of polarity? Yeah, so if it's the same on both sides, you can actually expect some like canceling go on and have some less polarity there. So in this case, these are made of the same types of atoms, but the big difference here is that the one on the right, or I'm sorry, the one on the left, has this OH there. And we know that OH is a really strong, strongly polar thing, and would therefore probably lead to this hydrogen bonding, which only happens if that OH or NH is inside the is part of the molecule. So even though that second example is still made of O's and H's, because there's no actual OH bond, we don't have that same possibility of hydrogen bonding. So the second molecule actually is also polar because of that oxygen. You may not have known that because the way I drew it kind of makes it look like it would cancel out. But in the actual molecule, it's more kind of zigzagged. It's not quite canceled out. So there is a little bit of polarity, that second one, but not nearly as much. So if we look up the boiling points, the boiling point of this first one, which is called butanol, is 117 degrees C. The boiling point of the second one is 34.5 degrees C.
So that one, like a better force.
Much stronger forces for the one on the left because of that OH. But again, we have to make sure we're saying the reasons correctly. It's not that the OH bond itself is strong. It's that the presence of the OH leads to this hydrogen bonding situation where that molecule can attract other molecules like it in a strong way. All right, let's try another one.
So like, what do you look for before you start deciding if you look for the OH bond or just saying?
Yeah, you're looking for the types of intermolecular forces. So can they have hydrogen bonding? Can they have other types of polar forces? That has the biggest effect on the overall boiling point. I would say lowest to highest. Oh. All right, rank the following lowest to highest boiling point. Got CO2, CH3OH, methanol, and CH3Cl. Let me give you the structures for these so that you can see the sizes, or the shapes. So we did CO2 already, it looks like this. CH3OH is like this, basically, and CH3Cl is like that. So same thing, rank them and then discuss your reasoning, how you rank them in your group. And we'll talk about it all together.
Like Goose Island.
What?
You like Goose Island?
Goose Island? Oh. Okay.
Somebody wants to look this.
Yeah.
All right, you got some orderings yet?
Yeah.
In a minute. Okay. Which one did you say here would be the lowest boiling point?
CO2.
You said CO2? Why?
Bond itself could be easily put compared to the other ones.
What bond?
The CO2.
Okay. What bond is breaking though? What bond would break?
CO.
Okay, careful with that though, because if you break the CO bond, you've made a different compound. That is not boiling. Boiling is a physical change, so the compound needs to stay the same. So what is breaking when we boil CO2? Anybody? The intermolecular forces, right. So the attractive forces between CO2 and other CO2 molecules are the things that are breaking. And what types of forces would those be? Yeah, they'd be nonpolar dispersion forces. So CO2 is nonpolar. So we would expect it to connect via dispersion forces. What about the other two then?
All the way to the right, the second.
Yeah, so this one is polar. Right. So exactly. So the middle one is the highest boiling point because it has that OH bond, which allows that hydrogen bonding, which we know is the strongest way that molecules can attract each other. So that's going to have the strongest types of attractions. The one on the right is also polar because the CCl bond is polar, but only the standard polar forces like we saw in HCl here. So they'll still attract each other like this, but those forces aren't quite as strong as when there's an OH involved. And then the third one, as you all said, you're correct, is the CO2, which would only have the nonpolar dispersion forces. Any questions about that kind of thing? How to do that? Okay. Another thing that we can use intermolecular forces to predict is mixing or making solutions. So let's say we've got some water, like up here. Water is connected through that hydrogen bond network. I'm going to draw it in just sort of like a quick mini way, just so we can draw a bunch of it. We can draw like this. Do you get what I'm doing if I draw this like that? These are water molecules. So we've got our hydrogen bonds that are kind of connecting this whole thing in a network. A bunch of water molecules. That right? Okay, so there's our water. That's what water looks like in the liquid state. Basically, it's this. That picture. It's this. And nonpolar molecules are going to look similar, just using a different type of force. So if we take, let's take some nonpolar molecules, which I'm just going to draw as like squiggles. So Here's our nonpolar molecules. Big carbon-containing molecules like octane or something like that. So here's our polar hydrogen-bonded water molecules, and here's our nonpolar dispersion force connecting whatever's octane or something. So I'll use a red dots to indicate the dispersion forces that are connecting these things together. So there's the dispersion forces. And then in water, we have the green hydrogen bonds. In all of those cases, remember we talked about energy last Thursday, those are all stabilizing forces. The reason this happens is because when those molecules can attract each other through these forces, that stabilizes the whole situation. So polar molecules are stabilized by these hydrogen bond connections. Nonpolar molecules are stabilized by these dispersion forces. So we can predict whether these things are going to mix if they're moved together, if they're put together, based on the types of forces they would make. So if we imagine a substance like water and a substance like octane, like gasoline, or even something bigger like an oil, we know that we say they don't mix, but if we were to like physically, mechanically mix them, what we're doing is taking our nonpolar molecules, splitting them up, taking our polar molecules, splitting them up, and then sort of like putting them in between each other. So what types of forces is water going to have with these nonpolar molecules? Yeah, maybe some really weak dispersion forces, but not much. So those forces, all those nice network of forces, the green ones and the red ones, are now gone when we try to put these things together. So this is a much less stable situation than if these things were to stay by themselves. And so this predicts that these actually wouldn't mix, and that's what we see. And we'll do a lab about this next week also. This is what we would predict, that in fact the water molecules and the nonpolar molecules would not mix together because they would lose all their forces. So from all this information, we would say that polar and nonpolar molecules are unlikely to mix because they would have to abandon their own forces and they wouldn't be able to make new forces with the new connections. We can think about solubility in other ways like this too. So if you think about ions, think about like sodium chloride. When sodium chloride is put into solution, is put into a liquid where it can dissolve, it breaks apart into its individual ions, sodium and chloride. So now in water, these ions can be stabilized through these types of intermolecular interactions. Sodium is a positive ion, so we would expect water molecules to all kind of orient themselves with the negative side toward the sodium. Because we know that there's a partial negative on the oxygen and a partial positive on the hydrogen. And so we would expect these kinds of attractions toward there, which is what happens. In fact, I'm drawing it as a circle, but it's really a sphere that goes all the way around the ion. And then there's more kind of branching from there to other water molecules. Around the chloride, we'd expect the exact opposite. The positive hydrogens would point down toward the chloride. And interact that way. And then that would also kind of connect to the rest of the stuff. And this is how ions get dissolved in water. So the fact that that water can have a positive or a negative side allows it to encapsulate these ions and dissolve it. Would you expect that to happen in a nonpolar solvent, in a nonpolar liquid? Do you think that ions would be able to separate in a nonpolar liquid? Yeah, they would not, because those nonpolar molecules can't attract those ions, can't connect to those ions the way that polar ones can, because they don't have a positive or negative to match up with the different ion. So then we can also make another generalization, which is that ionic compounds dissolve better in polar liquids than in nonpolar liquids. Because the polar liquids can interact with those ions in a way that the nonpolar liquids cannot. All right, so that's two big things that we can predict just looking at molecular structures and judging the polarity of those molecules. We can predict the strength of the boiling point, how high is the boiling point, and we can predict whether things are likely to mix or not. There's a couple other ones that they mentioned in the book, and I'm just going to mention them. We're not going to spend much time on them. They're not as important. One is surface tension. So if you have a sample of a liquid, how strong is that surface of it? Like, you know, with water, you can like float a paperclip on top of water, or like a piece of grass or something that will actually stay on top because of the surface tension of the water. That also has something to do with how much it will spread out when you put a droplet down on the surface. Water will keep pretty tight, but nonpolar compounds, like nonpolar solvents, like gasoline or something like that, would spread out more. Oils also. You can also predict viscosity, which is how something resists flowing. So something that is very thick, something like a sugar syrup, that has a lot of those strong forces, flows very slowly like honey. But something that has much weaker forces, like some of the organic solvents that we'll use throughout the class, one that we'll use next week, flow very quickly, so much so that it's sometimes hard to hold them in a pipette or a dropper. So that's another thing that can be controlled by intermolecular forces. These both have a lot more going on than just that, so that's why I don't want to spend too much time on them. But from a rough approximation, you can use IMFs to predict how strong those forces are going to be, or those effects are going to be. All right, so questions about this stuff? So things you should be able to do from this are look at a molecule structure, determine if it's polar or not, determine if it can hydrogen bond or not, and then use those ideas to predict boiling points, to judge relative boiling points. You can do that, maybe with a little practice. All right. We'll stop there. So if you haven't had a chance to print out the instructions for lab, please do so. You'll see that this lab is a little bit more open-ended than the previous ones, so we'll talk about it a little bit when we get started at 2, and then we will give it a try. No.
Oh, not yet.
No. Thursday, probably. Thursday. If I get them done. Otherwise, next week.
Okay, sounds good. And my grade, I did the homework too, the online homework, but it's
okay.
not.
Yeah, I haven't changed anything with that yet.
Sounds
It's just working on the exams. I'll get it changed for you.
Okay.
Just keep reminding me if I haven't changed it.
Oh yeah, thank you.